Welcome to The Explainer. Today, we're grabbing our magnifying glasses and putting on our detective hats because we're about to investigate the world of database normalization. We're going to crack the case of messy data and uncover the clean, organized truth that's hiding inside. Okay, let's just dive right in with a really important question. See, disorganized data, it's not just a minor annoyance. It's more like a ticking time bomb, just waiting to go off with all sorts of errors and inconsistencies.
So these three things you see here, these anomalies, they're the main culprits we're hunting down. Think about it. An insert anomaly. That means you can't even add a new student to your database unless they're already in a course. Kind of weird, right? Then there's the update anomaly, where you have to change a student's name in like 10 different places. And the delete anomaly? Oh, that one's nasty. That's when you drop a student's only course and poof, they're just gone from your records entirely. So normalization, that's our toolkit for solving this whole mess.
So to guide our whole investigation, we're going to use three really simple but super powerful questions. This first one, it's all about our number one suspect, redundant information. We're going to find it, and we're going to eliminate it. Next up, our second question. This one helps us uncover some of those shady, hidden relationships inside our data tables. You know, it's all about making sure every piece of data is exactly where it's supposed to be, answering directly to the primary key, and nothing else. And finally, our third question. This is the one that really pushes us to get everything organized in the most logical way possible. It's all about structuring our evidence, the data, into clean, separate, logical concepts. Okay, let's get to it. The investigation officially begins, and using that first question, we find our first big clue right away, repeating groups of information. And that, my friends, is a huge violation of something we call first normal form. Just take a look at Exhibit A here. See that courses column for John? We've got two completely different courses, DB and networking, just crammed into one cell. That is a classic textbook sign of trouble. It's a total violation of our first rule. So the rule for first normal form, or 1NF, is actually super simple. Every single cell has to contain one and only one atomic value. Atomic just means it can't be broken down any further. The analogy I like is an evidence bag. You put one piece of evidence in each bag. That's it. And here you go. This shows the fix perfectly. We just split John's courses into their own rows. And now look at that. Every cell has a single atomic value. The data is so much cleaner, way easier to work with. And just like that, we have officially solved for 1NF. Case closed on clue number 1. All right, let's move on to our second question. Now, we're looking for something a bit more subtle, improper dependencies. This is where data starts relying on the wrong clues, and this part of our investigation is going to take us through both second and third normal forms. Okay, take a look at this table. The primary key here is what we call a composite key. It's made of two parts, the student ID and the course ID. Together, they uniquely point to one single enrollment. But look at the student name. Does a student's name really depend on which course they're taking? Of course not. It only depends on their student ID. This right here is called a partial dependency, and trust me, it's a big problem. So the whole point of second normal form, or 2NF, is to get rid of these partial dependencies. Every other piece of info in that row has to depend on the entire primary key, not just one little part of it. And how do we solve it? Well, we split the table up into smaller, more logical pieces. We make a students table, a courses table, and then a third table, enrollments, that just links the two. Now, student name is in the students table where it belongs, depending only on student ID, and course name is in the courses table. It's clean, it's perfect. But wait, the case isn't quite closed yet. Check out this new piece of evidence. The major name, like computer science, depends on the major ID. Okay, that makes sense. But the major ID depends on the student ID. So you have this indirect chain. Student ID points to major ID, which then points to major name. That, folks, is what we call a transitive dependency. This is where third normal form comes in. It takes things one step further. Our job now is to hunt down and completely eliminate these indirect transitive dependencies. The rule is really direct and simple. Every column that isn't part of the key must depend only on the primary key. Period. Nothing else in between. And you guessed it, the solution is another clean split. We just create a totally separate table just for majors. So now the majors table holds the major name, which depends directly on its key, the major ID, and the students table, it just needs to keep track of the major ID. No more indirect chains, problem solved.
So now we bring in our third detective question. Can I break this down even further? This is where we get into some of the more advanced stuff. Let's take a quick look at a couple of advanced forms for when a case gets, really complex.
First, there's Boise-Codd normal form, or BCNF. You can think of it as a much stricter version of 3NF. It's for these rare but really critical edge cases where a table might have multiple possible primary keys, we call them candidate keys, and they overlap. In these weird situations, a column that isn't even a key might actually determine part of a key, and that's a huge no-no we have to fix. Now, this is really interesting because it shows a key difference. Remember how 3NF fixed that indirect dependency chain? Well, fourth normal form, or 4NF, it tackles a totally different beast, something called a multi-valued dependency. So imagine a student has a list of their hobbies and a totally separate independent list of languages they speak. If you try to cram all that into one table, you end up creating these bizarre, meaningless combinations. You'd imply that soccer is somehow related to Spanish for that student, which makes no sense. 4NF solves this by, you guessed it, splitting them into separate tables.
Okay, so we've solved all the clues. But how does a real-world database architect decide how far to go with all this? When do you stop? Let's take all this theory and turn it into a super practical decision-making flow.
This table right here is basically our entire case file all wrapped up. It shows you exactly which problem each normal form is designed to solve. We start with 1NF, getting rid of those repeating groups, and go all the way up to 4NF, tackling those multi-valued dependencies. Each step just brings more clarity, more integrity to our data.
Now, this right here is the key takeaway. In the real world, for most systems, your target is going to be third normal form. That's the gold standard. Once you hit 3NF, you just ask yourself two final questions. First, do I have one of those rare overlapping key situations? If the answer is yes, you might need to go to BCNF. And second, does one of my records have multiple totally independent lists of things attached to it? If yes, then you need 4NF. Following this simple flow keeps your database squeaky clean without making things way more complicated than they need to be.
And just like that, our investigation is closed. Normalization gives us this beautifully clean, totally reliable data structure. It gets rid of all those hidden dangers and makes sure our data is solid. But, there's always one final step for any good detective. You have to make sure that all your perfectly organized evidence is actually telling the right story. Because really, what good is clean data if it doesn't lead you to the right conclusions?